Now, our last theorems for circles is what we call the part of the secant theorems. So, what we've got here, we've got intersecting chords, which could form secants, I suppose, because they're cutting 2 points. But so the idea here is if we've got intersecting chords, that where they cut off, so AE and EB times CE times ED would be equal. Now we do these by similar triangles. So if we have a look and we've got these two diagrams, if we can join up AC and BD. So in this triangle AEC, we get the angle AEC is equal to the DEB there, because they're vertically opposite. And we also get that CAE, angle CAE, so this angle here, would be equal to this angle here. So we'll put a little cross in those. There, so it's equal to BDE, sorry, yep. So those two angles are equal, and because they're on the same arc, BC is the arc that's causing them, it gets the angle there, it gets the angle there. And then you've got angle ACE and angle DBE, which are going to give them the same, because they're on the arc AD, they're subtended by the same arc there, so they're going to be equal as well. We already had two, we only needed two there to prove that these two triangles are similar. Which means that if we get AE, that must on ED, they must be in the same ratio as CE and EB. And if you then cross multiply them, we get the AE times EB would equal CE times ED. So there's your proof of that theorem. Products of the lengths of segments of two intersecting chords are equal. In the second one, this time we're going to do it pretty much the same way, but we've got two secants. And what we want to prove is that where the secants cut off, SA times the cut off part in the circle, SB, would equal SC times the cut off part in the circle from that secant, CD. So again, we draw up AD and CB. We want to find some similar triangles. So we look at the angle BSC, so BSC, so this angle would equal DSA. Well, that's the same angle. DSA, BSC. So there's one angle in two triangles that is the same. And we also get SBC, so this angle here, SBC, because it's sitting on the same arc there, that angle there would equal SDA, because that would be in the same arc, because it's created by the same arc, AC. So there's two angles in each triangle that are similar, so they must be similar triangles because they're equiangular. So thus, that slide SA on SC, because they must be in the same ratio, and these sides here where we've got SD, so SD of the triangle, and SB would be in the same ratio. So therefore we can say SA times SB, and it must be equal to SC times SD. So part where it's cut out across the whole secant, and then part times the part cut out here by the whole secant there. So that's a second theorem there. And the last one is where we have a tangent to a curve and then to the circle, and then we have another triangle here, another line here, which is the secant. So the square on this side here, PT, would be equal to PA times the whole secant PB. So again, similar triangles are where we're going about this. So we join up, we get PTA. So would that be equal to PBT, because PBT. So it's that TPA and BPT, same angle. We get it right to start off with. And then PTA, this angle here, would be equal to ABT, because this angle here that's marked there, because of the alternate segment theorem. So therefore they're equiangular. So you've got two angles in one equal to two angles in another. So PT here on PB, so you look at where the angles are common. So PT on PB would equal PA on PT, because that would be in the same triangles as well. Therefore, you can rearrange that to multiply the PTs to get PT squared and PA times PB. So there's the third one, the square of the tangent to a circle equals the product of the intercepts of a secant from the same external point. So the pt squared would equal PA times the whole secant PB. So there's the three theorems. That's the last of the theorems. Now you know all the theorems for circle geometry. That's a little bit exciting. You've just got to get used to applying them all. They're not easy. As we said, there's lots of them. It only says theorem 14 here, but with the converses, it's about 22 all up. So be wary of them, be able to use them, be able to recognize them. It takes a lot of practice to do that.